Okay, so at this point, hopefully, you're able to solve radiation problems where you have, n surfaces, where n can be pretty much any number. You understand the methodology for setting up your sets of equations, and at least the concept of what the view factor is. And you can do this for black surfaces, obviously, but you can also do this for gray surfaces that are diffuse, right? So you can do this for surfaces that aren't black, but there's some pretty severe limitations on their emissivity. So the last two topics are going to help you tackle more realistic radiation problems. So today we're going to talk a little bit about semi-gray surfaces, and that's going to let you deal with surfaces that have more realistic emissivity functions, emissivities that depend on wavelengths in some arbitrary way. And then the next time, our last topic will be the Monte Carlo technique. And the Monte Carlo technique is really cool. We are only going to really use it and introduce it so that you can come up with view factors, but it can be used to do entire radiation problems. We'll talk about that next time. But for today, we're going to talk about semi-gray surfaces. So the idea behind semi-gray surfaces are that we're no longer requiring that the emissivity be constant. We're no longer requiring that the surface be gray and that the emissivity is constant along all wavelengths. Instead, we're saying, we're going to allow you to simulate a surface that has emissivity that's constant in different wavelength bands, right? So I can make these bands that are shown here as small as I want and have as many of them as I want in order to simulate a surface that has an arbitrary variation of its hemispherical emissivity. All right, and so that's a very powerful technique. Within each of these bands, we're going to do the same gray surface radiation calculations that we talked about last time, right? So we're really just splitting this problem up into a whole bunch of wavelength bands and dealing with each band separately. And then at the end, we can add up what's going on in each band in order to understand what's going on with the surface as a whole. All right, so here's a semi-gray surface. I have n sub b wavelength bands, right? So the first thing we got to get comfortable with is the fact that I now have n surfaces. So I'm going to have a subscript that talks about each surface, and then I'm going to have n sub b wavelength bands. So I'm going to have another subscript to talk about each wavelength bands, right? So I is going to be the subscript that we use to indicate the surface, right? I equals 1 to n, and w, so this w right here is going to be the subscript that I use to indicate the wavelength band. So w will go from 1 to n sub b. And this is just the way we have it here, right? Each wavelength band is defined by a lower limit on the wavelengths, so lambda low, let's do this one, lambda low sub w, and a higher limit on the wavelengths, so lambda high sub w, and within that band you have one emissivity epsilon sub w, right? And you have to go from 0 all the way up to some really high number in order to capture all of the radiation. So that's the idea behind a semi-gray surface. Just to remind you, at this point, hopefully you're really good at simulating gray surfaces, right? A gray surface is one where I just have one band, right? N sub b is 1. The lower limit of that band is 0, and the upper limit of that band is infinity. And I write this set of equations here for that band, that one band, right? So all I'm going to do now is expand this set of equations and write it for every single band. That's all the semi-gray surface does, is it takes the same set of equations and it just adds another subscript to those quantities that are unique to each band, right? So that's what this looks like right here, right? I have these same 2n equations, but now I'm going to write them for each wavelength band. So you'll see here, I'm writing this set of equations right here. I'm writing that set of equations right here for every surface and for every wavelength band. And the same thing for the second set, right? Here's the second set of equations. I'm going to write those for every surface, and I'm going to write them for every wavelength band. So wherever you see an I here, that's indicating the surface, and wherever you see a W here, that's indicating the wavelength band. This J should really be a W, I'm sorry. Okay, so that's as simple as it gets. Easy to say. The tricky part of this is keeping in your mind then what each of these different symbols actually means, right? It's relatively easy to write the equations. You're going to put these in a duplicate loop and then put them inside of another duplicate loop, so you'll have a nested set of equations. But remembering what each of these symbols actually means is something else. So let's start with let's start with the easy ones. A sub I, that is the area of surface I. You'll notice that I don't need a second subscript W on this because the area of surface I in every wavelength band is the same, right? I don't need to redefine it over and over again for each of these wavelength bands. The other one is pretty easy to understand, I think, is epsilon IW. So this is the emissivity for surface I in wavelength band W, right? So for example, I would have a picture like this that would give me the emissivity in every wavelength band, and I have a picture like this for every single surface, right? So this would be epsilon for surface I in wavelength band W, epsilon IW. So those are pretty easy. Maybe the ones that are a little more tricky are the ones that I've listed here. So Q dot IW, this is the what? This is the net radiation heat transfer from surface I, so this is surface I, that occurs in wavelength band W, right? So when I solve this set of equations in any one wavelength band, I'm getting Q dot IW, right? I'm getting the net radiation heat transfers for surface I, but I'm only getting the part of it that happens in that certain wavelength band, right? If I want the total radiation heat transfer that happens for surface I, which I am going to want for sure, right? That's going to be either a boundary condition or the primary purpose of putting the whole model together is to predict that. How do I get that? Well, I have to take the value that occurs in each of these wavelength bands and I have to add them all together, right? So Q dot I, this is the net radiation heat transfer from surface I, is the sum over all of the wavelength bands of Q dot IW. Right, so from 1 to n sub b, I sum these up. And it's kind of cool, actually. You'll see sometimes that in some wavelength bands, your surface has a net radiation heat transfer from it, whereas in other wavelength bands, it might have a net radiation heat transfer to it, right? But you add them all up, and that's the net radiation heat transfer from surface I. All right, so we have A done, we have epsilon done, we have Q dot done. How about this guy right here? This is E sub B IW. So this is the blackbody emissive power, right, that occurs for surface I. So previously, when I had this set of equations, this was the blackbody emissive power for surface I. This was just sigma Ti to the fourth, right? This was over all wavelength bands, how much did my blackbody emit, right? Well, when I add a W now, I have to be a little careful. This is the blackbody emissive power for surface I, the part of it that occurs within wavelength band W. So if I add up all of my EBIWs over all of my wavelength bands, I better get sigma T to the fourth back. But within each wavelength band, I'm going to have a smaller amount of blackbody emissive power, right? So that's given by this equation right here. It's EBIW is the spectral blackbody emissive power, so this is Planck's law, integrated from the lower limit of that wavelength band, so from lambda low for that wavelength band, up to the upper limit for that wavelength band, so up to lambda high for that wavelength band, right? So this is the integral I'd have to do. One of the reasons we talked about this function in E is called blackbody is basically that it does that for you, right? So this blackbody function gives you the fraction of the amount of radiation emitted by a black body at this temperature that occurs between these two wavelength bands. So EBIW is just black body called in this way, and I didn't put this on here, but it's important that you actually multiply this by sigma Ti to the fourth, right? Sigma Ti to the fourth. This is a dimensionless thing. EBIW has dimensions of watts per meter squared, so I need to multiply this by sigma Ti to the fourth. Okay, so I'm almost done. The last thing to see here is this JIW. So this is the radiosity from surface I that occurs in wavelength band W, right? So this is actually physically how much radiation per unit area is leaving surface I. And it's not all of it, it's just how much of it happens in this little wavelength band window that we're talking about. So that's the way that you that's the way that you solve these problems. It's actually as simple as this, right? You have to start by now calculating, again, all of your view factors. You'll notice they don't care what wavelength band they're in. We're still dealing only with diffuse surfaces, so these are all just going to be view factors the same way that they were before. You calculate all your areas. That's pretty easy. You set up now a matrix that contains the emissivity for every surface in every wavelength band. That's something that you should be able to do. It should be part of the problem specification. And then you implement these equations, right? And if you couple these equations with a complete set of boundary conditions, so that would be temperature of each surface or heat transfer rate for each surface, and I don't mean heat transfer rate in any one wavelength band, I mean this net heat transfer rate for every surface, you should have a sufficient number of equations to solve. Now, I'll warn you that converging to a solution happens much easier if you initially set the temperature of every surface, even if that surface has a specified heat transfer rate. So the way to do this to actually get a solution that works is you set the temperature of every surface. You can then solve this set of equations if you've set them up right. It will give you the rate of heat transfer every surface, and the last thing you would do then is adjust the temperatures in order to get the rates of heat transfer you want for those surfaces where that's your boundary condition. And it actually works pretty easy. It's pretty cool. Let's look at this for a specific situation. So one more time back to this transfer line, right? At first we did it as if all the surfaces were black. Then we got smart enough to do it as if all the surfaces were gray. So now we can do it where these surfaces are actually semi-gray, right? So I have this surface here. This inner surface has an emissivity of 0.9 for this band, so from 0 to 22 microns, and then 0.5 above 22 microns. And then epsilon 2 is still just 0.5 over all wavelengths. Epsilon 3 is 0.7 over all wavelengths. And epsilon 4 now, it is 0.8 from 0 to 8 microns and 0.2 from 8 microns and above, right? So these two surfaces have two different bands of behavior, right? 0 to 8, and this one is 0 to 22. So the problem as a whole actually needs to be broken up into 3 bands, right? Because I have to, in every band, every surface has to have a constant emissivity, right? So if you think about it, from 0 to 8 microns, I have one set of emissivities that characterize all 4 of these surfaces. From 8 microns to 22 microns, I have a different set of emissivities that characterize all 4 of these surfaces. And then from 22 microns and up, I have still another set of emissivities that characterize all these surfaces, right? So the way that we're going to do this in ease then is we're going to take our previous solution, right? We're going to enter the emissivities. They were a vector. Now we have to make a matrix, right? And the matrix is going to be 4 by 3, 4 surfaces, 3 bands. The areas and the view factors, they aren't going to change at all. We're going to set the temperatures and determine the blackbody emissive powers within each band. And we're going to use this equation here. Again, I forgot the sigma ti to the 4th, but that needs to be here as well. We'll hit solve and we'll be able to get a solution. And then the last thing we'll do is we'll determine the total rate of heat transfer within each band for each surface. I'm sorry, the total rate of heat transfer for each surface. Oh my God, this is not my most mistake-free lecture ever. I'm sorry, but this should be for each surface. So Q dot I, we're adding up all of the heat transfer rates for every band, and you get the heat transfer rate for each surface. And then finally, as needed, we will adjust these temperatures in order to get the boundary conditions that we need on the heat transfer rate. So that should be hopefully what I've got here. So if we go up to the top here, these are my emissivities, right? Hopefully this makes sense. This is the emissivity for surface 1 in the 1, 2, 3 bands, surface 2, surface 3, and surface 4. I have to set the limits for each band, so 0 to 8, 8 to 22, and then 22 to, obviously I can't do infinity, but I got to do some big number that will capture all the radiation. Here are all the view factors. This hasn't changed at all. It's exactly the same thing we did before. The next thing I'm going to do is set the temperatures. Now, T1, 3, and 4, I know those temperatures are my boundary conditions. T2, I don't really know. So I just set it to some reasonable guess value, and doing that then allows me to implement this set of equations here, where for every surface and in every band I calculate the blackbody emissive power, right? So this is EB for surface I that occurs in band W, and I evaluate that using the temperature of surface I, and then this is the wavelength band limits, and then sigma Ti to the fourth. And this last set of equations are my two sets of equations that I have to do, right? So this is in each band, this is my surface resistance equation, and in each band, these are my radiosity equations, right? And at this point, I can hit solve and get a solution, I hope. So here's my solution, right? It gets to be large, but you can see all of what's going on here. The calculated thing, so I set my temperatures, which means all of these things are inputs, all of my blackbody emissive powers. And so what I'm calculating really then are all these heat transfer rates. This is for surface 1 in band 1, surface 2 in band 2, and surface 3 in band 3. So the last thing I'm going to do then is add these up. This is my total rate of heat transfer for surface 1, for surface 2, 3, and 4, right? So I'm almost done. The one thing that's wrong is this rate of heat transfer for surface 2 should really be 0. And this temperature then needs to be whatever it is such that this is 0. So right now I've made this temperature a little too cold, right? This is a net rate of heat transfer into that surface when in fact that should be 0. So if I make this surface a little hotter, I should see this approach 0. And I can do that manually, or I can just come in here and set my guess values, which I've done right here, and then comment this out. So I'll comment this out. And then I'll go down here and just require that Q dot total 2 is equal to 0. And if I've done a reasonably good job with my guesses, I should see that now it'll tell me Q dot, so temperature 2 should be 233.4, and that gives me that 0. And now I have my solution. So this is my solution. You know, it's kind of cool if you look at surface 2, for example. You can see that actually in band 1, so in that lower wavelength band, it's receiving radiation, but in bands 2 and 3, it's actually emitting radiation. There's a net amount of radiation coming from it, right? So you can see sort of what's going on in each band individually, and you're dealing with packets of radiation now that are collected spectrally, right? So this is actually a really cool, powerful way of dealing with surfaces that are not, you know, these really simple gray surfaces. And like I said, next time we'll talk about the Monte Carlo technique, just enough so that hopefully you understand it and you can use it to get view factors for surfaces that aren't as simple as the ones that you'll find in the library. And if you're armed with these semi-gray surface solutions in the Monte Carlo technique, you can really tackle most radiation problems that you'll encounter in your career. If you get to situations where the surfaces are not diffuse, then these tools won't work, right? You have to have surfaces that behave uniformly in all directions. If you get to a situation where that's not the case, now you're really going to get into more sophisticated Monte Carlo type ray tracing solutions that are beyond the scope of this class. But I think how they work should be understandable to you.